am Mr. Kramer, of course, and I think I must have moved my computer. I had this squared away better than I did so you could see the whole board. I'm planning to give you guys a lecture on static electricity today, if I could speak. Static electricity. I'm hoping to remember to begin with prayer, so let's do that. Lord Jesus, you have our backs. You are here along with our guardian angels, and I thank you for being here with me and with my students, my physics students. We are beginning a new era. Here's Mr. Kramer on a technical, using technology that he's brand new to, interested in providing a decent fourth quarter, even though we're having to do distance learning, because that's what physics is for. And I'm happy to talk about electricity, and especially static electricity, here in this lecture. I'm in chapter 20. Thank you, Jesus, for your help and for remaining here with us as we talk. So this is the pretty picture on static electricity in your textbook. It's on page 546. You guys have an outline of chapter 20 that's due today. So I hope that it works out for you, that you're able to get that done. Feel free to write it down while you watch this movie. It certainly makes sense to me. So electric charge. Of course, you've touched a metal doorknob and you felt a shock, especially when you've been walking around on carpet a lot. So there is that is an evidence that charge exists. Electric charge does exist. So we talk about, first of all, to get us into the mode of what is electricity, and it's actually electrons moving from one place to another. Electrons move for various reasons. I'll give you an example of an electron moving right off the bat, okay? Here's a balloon. Now, obviously, I am pressurizing the inside of the balloon to a pressure that's greater than the atmospheric pressure that's pushing on the balloon. The atmospheric pressure being 14.7 pounds per square inch in my room here, in room 320 of Greenwood Christian Academy. This balloon now has slightly greater pressure. It's probably not 1 psi. It's probably just measured in inches of water column pressure. But it is pressure, higher pressure on the inside of the balloon than the outside. And this is a rubber balloon. So watch this now. Here we go. I am convinced that video cameras make me look fatter, just so you guys know. So really, don't forget that I'm actually skinnier than I look just now. Did that get it? Sometimes when the humidity is high, you won't get static electricity to work. And why is that? Does anybody know? Why is it that when static electricity is being created by rubbing rubber on human hair, or sheep hair, or animal hair of any kind, why is it that static electricity doesn't always work? Look at that. Okay, it's because water molecules are bipolar. They have a center of charge. Here's an oxygen atom, okay? And here is 2 hydrogen atoms, sort of kind of attached to this oxygen atom. Okay? Can you guys see that? Barely. Sorry about that. So these two oxygen atoms, I'm sorry, this is an oxygen atom and these are two hydrogen atoms. I'll do this. Okay? Now, what's happening here? You know that oxygen has a greater affinity for the electrons that hydrogen has. And so, because oxygen wants two electrons really bad, and hydrogen is willing to give up its electron, single electron, they share these electrons, and the electrons mostly reside in the oxygen. So the oxygen becomes negatively charged, and the negative center of charge is right there in the middle of the oxygen atom. And then the center of positive charge on an H2O molecule is right there, because it obviously has two protons in each hydrogen atom. So, because this has a negative and a positive bipolar centers of charge, it can orient itself to neutralize charge. Okay? And that's why when it's humid, oftentimes you don't get static electricity to do this. But it's not too humid today. I had to rub it on my hair more than I thought. Sometimes you don't have to rub it on your hair that much. So here's that balloon sticking to the wall. Why? Why does the balloon stick to the wall just because I rubbed it in my hair? Well, it's because the balloon, the rubber balloon, let me think about this. Does it give me the electrons, or do I give the electrons to it? Let me think about that for a second. The rubber becomes positively charged, therefore it gives me electrons. Boy, if I'm wrong about that, I am sorry. I'm trying to remember how it all works. I'm drawing a blank on whether the rubber takes the electrons or if the rubber gives up the electrons. I think the rubber takes the electrons based on a picture that I'm looking at on page 551. You see the rubber tennis shoes at the top of page 551 right here? Okay? So here is before you've been rubbing, and here is after you've been rubbing. And you'll notice there's a lot of negative charges on the carpeting, and then the negative charges are up here on the rubber. Okay? So I am sure that the rubber takes the electrons from my hair. My hair gives up electrons because the rubber has an affinity, and it's just friction. Now, that's friction at a molecular level, atomic level, you might even say. So, where do those electrons come from? Well, now I'm slightly positively charged. My hair, have you ever seen those pictures where people's hair sticks straight out because their hair is all the same charge all of a sudden? And of course, similar charges repel. And so your hair sticks out and starts repelling. You can do that with a whole bunch of balloons. You can rub so many electrons off of your hair that you end up with positively charged hair that sticks out. I'm sure you've seen it. Van der Graaf machines are really fun, to touch and do that with your hair. You can find a video about that. There, look, it finally detached. So let's talk about that process real quick. The process of static charge. Okay? So enough moisture came over there to that balloon and the wall to get the balloon to detach. It neutralized the charge that was on the balloon. Okay? So what happens? You rub, you rub something, so negative electrons get on the something surface. There's still some positive in here too, of course. Positive charge doesn't go away. Positive charge remains. But you end up with more electrons than the positive charges in the vicinity where you've been rubbing. Okay? And here you have positive charges. still, but you have less negative charges. Does that make sense? Okay, here I've got a lot of negative charge. Here I've got both positive and negative charge. And so you understand, it becomes negatively charged. Now, bring this surface physically to a new surface. Okay, so here you've got a neutral surface. Positive, negative, positive, negative, positive, negative. And you're bringing this surface, I'm going to turn it 90 degrees now. Let's see, I've got positive, 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 and then I'm going to put twice as many negative charges here. Negative, 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 negative. Okay? So I've got more negative charge here. So what does that do? That pushes these negative charges away in the vicinity, deeper into the paint. This balloon is pushing the negative charges away, and now you've got negative charges next to positive charges, and so they attract each other. These attract. Okay? And this is an electromagnetic force. Force of attraction, just like in a magnet. Okay? So there's really, that's really all there is to it. There's something you want to also remember, and that is that only electrons are moving. When you're using friction to create static electricity, only electrons move based on contact. All right? So that's a microscopic view of what's happening. One more little concept here in section 1, talking about a conductor versus an insulator. Okay? So a conductor is something that it's easy for electrons to move across its surface. All right? That's what makes it a conductor. Copper wire. A copper wire allows electrons, and of course there's positive charges in copper as well. Every nucleus of a copper atom has many protons. Okay? The atomic, I'm going to go look at the atomic number for copper on the periodic table. 29. So there are 29 protons in every copper atom. Okay? And so, but these electrons here are easily motivated. When you put a voltage, notice this symbol I'm drawing for voltage. When you put a voltage on the wire, you are inducing, and this is the positive side and this is the negative side of this battery. All right? So you are pushing with your electromagnetic force of a battery, you're starting to push electrons in this direction. Okay? In a copper wire. And they can easily move. That's why they're a conductor. These electrons easily move from atom to atom. These outer electrons of all these copper atoms easily move through a conductor. Aluminum is a good conductor. Practically all the metals are good conductors. The outer, anything that wants to give up an electron, right, which of course the metals are, willing to give up an electron to something that wants an electron, like chlorine or fluorine or, you know, this positive side of the battery, right, wants to give up an electron to those things. And so that's how electric current works. The outer level electrons move in conductors easily. And they're called conductors because the electrons move easily. And I'm sure there's some level at which something switches from being a conductor to an insulator. Right? Now an insulator doesn't allow its outer level electrons to move. Plastics are holding on to their electrons far better than aluminum. Obviously, there's some resistance to electron movement, even in aluminum, but it's very low. relative to a plastic or a wood or, let's see, fiberglass, rubber. Rubber is an insulator. You can use rubber gloves to keep yourself from getting shocked when you grab the positive and negative of a high voltage battery. Anyway, I kind of like this being on the wall. You know, this video camera really makes me look fat. I'm going to have to rub it some more. All right. I wish Colton Yates were here, because if Colton were here, he'd probably rub this balloon with his hair until it got stuck to the wall for us all. So would Styles. Styles would love to do that. There we go. Look at that. Isn't that nice? Okay, so insulators. Insulators hang on to their outer shell electrons. They have an affinity for electrons, as a matter of fact, like rubber. Rubber has an affinity for electrons, and it becomes negatively charged in the vicinity of where I was just rubbing it on my hair, and then it pushes the negative charge in the paint away somewhat enough to create an electromagnetic effect to hold the rubber. So here's the insulator. Now, does the balloon, would the balloon attach to a piece of metal? Okay, that's an interesting question. I think that the balloon would not stay as long on a conductor, because I believe that the rubber would discharge more quickly even on a conductor than it does on a wall that's pretty much an insulator. Okay? So because the electrons don't move, it doesn't want to receive an electron either. So the static electricity can stay longer, or the electromagnetic effect can stay longer than if you were to try to attach a balloon to a conductor. Okay? So, insulators. Air will conduct electricity. It's called lightning. Okay? Lightning strikes. And that was a car driving down the road, in case you didn't notice in the foreground. All right. So we're going to end it there today, and tomorrow I'm going to talk about determining charge with an electroscope. Okay? And we're also going to talk about the force of attraction, Coulomb's law, on page 558 in our next video. And then we'll be done with chapter 20. I love you guys. Have a great rest of your day.